Okay, today I'm going to go through an A-level paper. This is the first ever international A-level paper on mechanics and materials for the new specification. So the first sitting was in January 2019, and I'm going to go through it probably in more than one video. Okay, so hopefully it won't take that long, but I'm going to go through it. I've underlined protractor because at some stage you do need a protractor. And if you're like my students, many of them don't have protractors with them. You do need them in physics exams if you need to measure angles. Okay? So here's the multiple choice questions. So section A is always 10 multiple choice. First question says, which of the following is a vector quantity? Well, work done is just energy used, time is not a vector, temperature is not a vector. So a nice easy question to start you off. Displacement is a vector. It's distance with direction. Number 2, which of the following is equivalent to 1 kilowatt hour? Kilowatt hour is a unit of energy because a kilowatt is power and hour is time. So multiplying a kilowatt of power by a time of 1 hour will be 1000 watts in energy times 3600 seconds. So that gives you 3.6 million joules or 3.6 megajoules, which is 3.6 times 10 to the 6 in standard form, which is answer C. Stokes' law is from the fluid section, materials. And Stokes' law can be used to determine the frictional force on an object moving through a fluid. Which of the following? Oh, that's why I've changed the word. I thought there was 2 missing. To which of the following would Stokes' law best apply? I didn't read it carefully and I put the 2 at the end. I thought they'd missed it grammatically. They'd put the 2 at the beginning. So to which of the following would Stokes' law best apply? And so a large sphere moving quickly through a fluid, if it's a large sphere moving quickly, it's likely to create turbulence. And Stokes' law is really only useful in laminar flow or streamline flow. Okay, so A is wrong. Again, B, a large sphere moving slowly will not be as turbulent, but a large sphere is likely to create some turbulence as well. So a small sphere, lower turbulence, but if it's moving quickly, the speed can increase the turbulence. So C is also incorrect, and D is the answer they're looking for, because it says to which of the following would Stokes' law best apply. Best apply means fits it the best. So small sphere, yeah, moving slowly will be the best application of Stokes' law. Okay, so Stokes' law is always with a spherical object, yeah, and the R represents the radius of the sphere, and it doesn't really work with anything else unless it's moving relatively slowly. That's 3 questions done. Question 4, a force of 90 newtons is used to push a box along a ramp of length 10 meters, as shown in the diagram, yeah, up to a platform. So the work is going in to get the box to the top of the platform, and the platform is 4 meters above the ground, and the weight of the box is 200 newtons. Okay, so there's 2 things you can work against. Physical force, mechanical work done, is work done against friction and work done against gravity. Okay, so the platform is 4 meters above it. The useful output is the gain in potential energy. Yeah, it's the height gain. That's what our useful output is. And the reason I'm telling you that is because the questions ask you which of the following expressions could be used to determine the efficiency of the ramp. So the useful output is getting it up 4 meters. Yeah, the input is all the work done against the friction and against the gravity. So the work done is 90 newtons by 10 meters. So it's 90 times 10, because it's telling you that's the force and direction is upwards. So that's all the work you have to do to lift it, to push it up the ramp, so that the work done is the input. So the answer would be gain in potential energy, which is 200 newtons mg, times the height, 4 meters, so it's 800 at the top, or 200 times 4 at the top, and 900 at the bottom. So that's pretty efficient, if you think about it. It's 800 on top, 900 underneath, so it's 8/9, so whatever that is as a percentage. So about 88 point something percent efficient. Okay, now the next question is about Newton's third law. So when two objects interact, they exert forces on each other. That's always Newton's third law. Which of the following statements is not a correct description of these forces? For those of you new to A-level, they always tell you when there's a not. They always put it in bold so you don't misread the question. Which of the following is not a correct description of these Newton's third law pairs of forces? The forces act at the same time. In Newton's third law, they always act simultaneously, so that means at the same time. B, the forces act in the same direction. No, because they're on two different objects. Action and reaction are always in opposite directions. That's what it means, action, reaction. If you remember when we did it in class, we used the skateboard idea. If two people on a skateboard, they push each other, one goes forwards and the one goes backwards. Okay, same with ice skates. So B is not correct. Yeah, the forces do not act in the same direction. And then you can see that the other ones are correct. The forces act on different objects. Yes, that's true. They must always act on two different objects. And the forces have the same magnitude. They have the same magnitude, but the opposite direction. So B is the only one that you can put as the correct answer. Question 6 is about SUVAT, the kinematics equations, constant acceleration formulae. A ball is thrown vertically upwards. Which row correctly describes the magnitude of the initial acceleration of the ball and the magnitude of the acceleration at its maximum height? So you've thrown the ball up. First, the initial acceleration is going to be due to gravity. And when it's at that height, maximum height, it's about to turn around and come back down due to gravity. So it's always G, and therefore the only answer that you can put is C. Number 7, it says one end of a 50 centimeter length of wire is attached to a support. Okay. So basically, presumably it's a wire that you're going to stretch. A load is attached to the free end of the wire, which extends it by 2 millimeters. So remember, one's in centimeters, the other's in millimeters. So the best thing is to put them both in SI units, which is meters. Which of the following is the strain? Well, strain is the extension over the original length. I think they call it delta x over x in this syllabus, Edexcel International. So it's 2 times 10 to the minus 3 divided by 50 times 10 to the minus 2. So all you've got to do is make sure you don't make an arithmetic error, which I don't think I have. 0.002 divided by 0.5 will give you an answer of 0.004. Dividing by half is the same as multiplying by 2. The answer is A. Question 8, again, a ball is dropped this time, so it's kinematics again, and bounces once and is then caught. So it's going to be finishing off at a constant height value. Okay, so at the end it will reach a certain energy non-zero because it's caught as it bounces. So it will be at the height of the bounce, maximum will be the height of the bounce. So it bounces once. It doesn't say that it's caught at this maximum height, but obviously it's not going to go as high as when it was dropped, because as the ball is dropped, it loses gravitational energy, and then when it bounces, it gains gravitational energy, and then it's caught, so it's going to reach a certain amount. So which of the following graphs of gravitational potential energy, E-grav they've called it, against time would represent the motion of the ball? So I'm not sure any of them are 100% correct, but we know that it's got to decrease first and then increase. So it can't be B or D, because B is not decreasing at the beginning, and neither is D. They're both increasing at the beginning. So it has to be A or C. It can't be C, because the rate of loss of height, I've written it badly. The rate of loss of height, or gain of height, I've put, increases close to the bounce. Yeah, so it speeds up as it falls because it's accelerating. So the rate of loss of height will be steeper as you get close to the bounce. So both sides next to the bounce should be steeper, which means it can't be C, so it should be A. But I think I would have been happier if they'd made the final part of after the bounce less potential energy than the initial potential energy. That's my only criticism of this question. So you're assuming it bounces to the same height. Then the next question is about the stiffness constant and Young's modulus. Yeah. These are terms used in physics that you know if you've studied the materials topic. Which row of the table shows the correct application of these terms? Okay. Now, Young's modulus is a constant for a given material. So we know it must be, for Young's modulus, the column under which is written Young's modulus, it must be for a material because it's fixed for a material. A Young's modulus is not about objects. So, for example, the Young's modulus, the two materials usually used in AS level are copper and steel has a higher Young's modulus than copper. So it doesn't take into consideration the dimensions of the object. Whereas stiffness, for example, if you got a thick wire versus a thin wire, it's the object, the two wires, which will have different stiffnesses, not because of their Young's modulus, not because the material that they're made of. They could be made of the same material, but one could have a greater stiffness than the other because of its dimensions. For example, it's thicker. Yeah, so both could be made of steel, and one object will be stiffer than the other based on its dimensions. So stiffness depends on the object's dimension as well. Example, length or thickness, or cross-sectional area, I should have put. Okay, so it must be an object for the first column and materials for the second column, so the only one which with two correct answers would be D. Finally, the question 10. It's a more difficult question for you to do. It's mathematical. A student uses a balance to measure the mass of a small cube with sides of length x. So we know that it's x cubed, the volume. We know the mass is 50 grams, and you would look at the second one. The student also measured the mass of a larger cube, which is 1.5 times the length, and therefore the width, and therefore the height of the first cube. So it will have a volume of 1.5 times 1.5 times 1 times 1.5 times the first one. So m is constant for both of them. You'll notice they're both 50 grams. So you can equate the masses, and you've got to work out the density of the second one, of the larger cube, in terms of the density of the smaller cube. Now, obviously, if the larger cube has the same mass, then it must have a lower density for the larger volume to equal the same mass as the smaller cube. So the smaller cube must have a greater density. So the way to do it is how I've done the algebra on the right. Yeah. So you put density equals mass over volume. So for the first one, it's just m over x cubed. So then you can change the subject to make it m, because both m's are known. So if you look at what I've done, you will notice that the mass here and the mass here are going to be the same mass. They're both 50 grams. Okay, so the only difference will be the volume is 1.5x cubed yeah? So you're cubing the x and you're cubing the 1.5. 1.5 cubed is 3.375 if you do it accurately. So once you got the two masses, you can equate them, yeah? Which is what I've done down here. You equate them. The x cubes cancel out, yeah? And I've then rounded up to two significant figures because I've noticed the answers are given to two significant figures. And then if you just follow my elimination of the x cubes underneath, you'll see the density of the larger cube must be the density of the smaller cube divided by 3.4, but they haven't got that. So, but 1 over 3.4 is approximately 0.30, so the answer is D. Okay, I'm going to end this first video here. Do the multiple choice separately because I'm a bit peckish and I need to go and eat something, and hopefully I'll have enough energy to do some of the structured questions afterwards. So if you found this useful, and if you're kind enough to support my channel, please like the video to help with the YouTube algorithms. It makes it go to the top of the list for other students the more likes we get. Share it with your friends if they're doing a similar exam. It doesn't have to be your exam. For example, my students are doing the linear, but we're using the international A-level papers as practice exams, and they're going to leave the linear ones to when we finish the whole course for the year. Okay, so if you haven't subscribed, make sure you've subscribed so you get notified when other papers are uploaded. And I have got the first linear paper ready to do, but it will be for a year 13 student who I'm teaching who's doing the linear exam this year. Most of my year 13s are still doing the modular, okay? So thank you for watching. Hopefully see you in the next video. Bye for now. Okay.